Good morning, or good afternoon, or good evening, wherever you are, whenever you are. My name is Fernando Gama, and thank you very much for your interest in my talk. Today, I'm going to talk about the stability of graph neural networks to relative perturbations. And the reason why I'm going to talk about graph neural networks is because I want to talk to you about machine learning on graphs. And the reason why I want to do this is because graphs are models of signal structure that describe network data. And network data appears virtually everywhere these days. It arises, for example, in problems involving teams of robots, where we have a communication network and the robots talk to each other to coordinate in solving some task. Or in smart grids, where we have the power network and we want to use the state of the grid to decide on power generation schemes. Or in remote sensing, where we have a bunch of satellites measuring different aspects of the same phenomena. Or in smart cities, where we want the different cars to coordinate among themselves to improve traffic. In all these cases, we want to leverage the signal structure in learning from network data. Successful machine learning on graphs requires an architecture that scales so that it can process data from arbitrarily large networks, exploits the data structure, allowing for fast training and moderate dataset sizes, and has a distributed implementation. This architecture is precisely that of graph neural networks. GNNs are built from graph convolutions that are local and distributed linear operations that generalize time convolutions. This makes GNNs appropriate generalizations of convolutional neural networks. GNNs defined this way are local and distributed, but this is certainly not enough to justify they are a good choice. We also need scalability. To get there, I will prove equivariance and stability properties of GNNs. Permutation equivariance means that the GNNs effectively exploit the data structure, while stability guarantees similar outputs on similar graphs. Together, they give us transferability and scalability. So the main result to discuss today is stability to perturbations, which guarantee that a small change in the graph support causes only a small change in the output of the GNN. Since GNNs are built upon graph convolutions, and these in turn are generalizations of time convolutions, let me take the license to remind you about regular convolutions. A convolution is a linear combination of shifted versions of the signal x. We shift the signal through time, and for each shift, we weigh by a different coefficient h. If we want to extend this concept to graphs, we need to have a notion of shift. This notion of shift is defined in graph signal processing to be a matrix description S of the graph. We see that we can describe this time signal as supported by a graph that is a directed path. Then, if we applied the adjacency matrix S of this graph to the signal x, we are indeed shifting the signal in time, or equivalently, shifting it around the graph. So the traditional notion of shift in time is equivalent to applying the shift S of a graph. Since now we have a definition in terms of a graph, we can extend this to arbitrary graph. Here we see how by applying the shift operator, we are gathering information from further away neighborhoods. So a graph convolution is a linear combination of shifted versions of the signal. But the effect of the shift operator is to update the signal with a linear combination of neighboring values. Thus, this operation is entirely local. Certainly, a graph convolution is equivalent to the application of a graph filter, and I will use both terms interchangeably. Equipped with the notion of graph convolution, we define graph neural networks. GNNs are a cascade of layers, each of which applies a graph convolution followed by a pointwise nonlinearity. So the signal goes in, gets filtered by this graph filter with these specific filter taps, and then it's fed into a nonlinearity. The output of this layer acts as the input to the next layer, where it is applied to another graph filter with different filter taps, another nonlinearity to get an output that then is fed to the next layer, and so on. The GNN depends on the filter's h, which we learn from training data, but also depends on the graph structure S. In summary, a GNN is a nonlinear mapping that exploits the underlying graph structure S. It relies on local information only and has a distributed implementation. Graph neural networks are nonlinear mappings that exploit the underlying graph structure S, rely on local information only, and have a distributed implementation. But is this enough to have a good architecture? It is not. As a matter of fact, there has been a lot of discussion on what is the appropriate graph operation to use. And this in part, I believe, is because beyond Euclidean domains, we cannot proceed out of intuition, but we need to operate from first principles. And what we do know is that GNNs are good at machine learning because they are translation equivariant and stable to small deformations of the domain. In graphs, translation equivariance is analogous to permutation equivariance, which allows GNNs to exploit internal symmetries of the graph. Stability to graph perturbations, on the other hand, implies that similar graphs yield similar outputs. These two properties in tandem lead to scalability and transferability. Recall the graph convolution operator is a polynomial on the shift, which depends on the filter parameters h, on the shift operator s, and is applied to the input signal x. Then we have that graph convolutions are equivariant to permutations. This means that for graphs with permuted shift operators and permuted graph signals, it holds that the outputs are permuted versions of each other. The proof follows from basic algebra and the properties of the permutation matrix. Recall that GNNs are graph convolutions followed by pointwise nonlinearities, but these pointwise nonlinearities do not mix node values. Therefore, GNNs retain the permutation equivariance property of graph filters, implying that signal processing with graph neural networks is independent of labeling. Invariance to node relabelings allows GNNs to exploit internal symmetries of graph signals. Take a look at these two graphs, where the nodes are identified with a number and the signals identified with a color. We see that both graphs have the same labeling, so they are the same graph, but the graph signals on top of them are different. However, if we take the signal in B, turn it inside out and rotate it 180 degrees, then we obtain the same signal as in A. So essentially, although different, signals on A and B are permutations of one another. And permutation equivariance means that the GNN can learn to classify B from seeing A, leading to faster training by leveraging the structure to learn multiple scenarios from a single sample. So we see that equivariance to permutation is more valuable than apparent. Permutation equivariance is a property of graph convolutions inherited to GNNs. Then why bother in adding pointwise nonlinearities to create a GNN? Or, more concretely, what is good about pointwise nonlinearities? And similarly, what is wrong with linear graph convolutions? Briefly, the problem with linear graph convolutions is that they can be unstable to perturbations of the graph if we push their discriminative power. The advantage of adding pointwise nonlinearities is that they make GNNs stable to perturbations while retaining discriminability. These questions can be better answered with an analysis in the spectral domain, which is a trademark approach of signal processing. Recall that a graph convolution is a polynomial on the shift operator with trainable filter taps hk. We can decompose the operator S as V lambda V Hermitian to write a spectral representation of the graph convolution as a projection of the output on the eigenbasis of S. What we obtain is that the graph Fourier transform of the output y tilde is equal to the same polynomial, this time operating on the diagonal matrix of eigenvalues, multiplied by the graph Fourier transform of the input x tilde. This means that the graph convolution is a pointwise operation in the spectral domain due to the diagonal nature of the matrix lambda, and that for a given input, the effect on the output is determined by the graph frequency response, which is a polynomial on each eigenvalue lambda I, all with the same filter taps hk. We can thus reinterpret the frequency response as a polynomial on continuous lambda. So we have this black solid line representing the polynomial given by the filter taps for all values of lambda, and here in blue the eigenvalues specific to the shift operator. The effect on the output comes from instantiating this frequency response on the eigenvalues of the graph. If the graph changes, the eigenvalues change, but not the frequency response. So the key insight here is that the frequency response is the same no matter the graph. The actual effect of the graph on the output is observed when instantiating the frequency response on the particular spectrum. Of particular interest are graphs that we call integral Lipschitz. These are graphs whose frequency response satisfies that lambda times its derivative is bounded by a constant c. Integral Lipschitz filters have to be wide for large lambda, because if lambda is big, h prime lambda has to be small. But they can be thin for low lambda, because if lambda is small, then h prime lambda can be big. Now, these filters are of interest because they are the ones that are stable to perturbations. What perturbations? Well, we measure perturbations as the relative distance between the original graph S and the perturbed graph S hat. We define it as the norm of the smallest matrix E that maps S into a permutation of S hat. Note that this distance measures relative differences between graphs modulo permutations. In particular, it is small if the graphs are close to being permutations of each other. Now we can get a stability result when the GNN consists of filters that are integral Lipschitz. Consider a GNN with L layers having integral Lipschitz filters HL with constant C. Graphs S and S hat are such that their relative distance is less or equal than epsilon over 2. Then it holds that for all signals X, the difference in the output between a GNN that runs on S and one that runs on S hat with the same filter coefficients is bounded by epsilon, which is in fact the distance between S and S hat. In essence, GNNs can be made stable to graph perturbations if filters are integral Lipschitz. We stated that graph neural networks can be made stable to graph perturbations if filters are integral Lipschitz. The GNN stability theorem is elementary to prove for an edge dilation, that is, when we multiplied edges by a 1 plus epsilon for a small epsilon close to 0. The effect of an edge dilation is to produce a spectrum dilation, where the eigenvalues of S in blue move to the eigenvalues of S hat in red. We then see that even if epsilon is small, the largest eigenvalue on the right can change a lot, causing a big change in the output of the filter. Thus, small deformations may result in large filter variations for large lambda. Integral Lipschitz filters, on the other hand, are always stable. Either the eigenvalues are small and therefore don't move much, or if they are large, then the filter is the one that doesn't move. This causes the output of an integral Lipschitz filter not to change much under graph perturbations. The problem with linear graph convolutions is that they cannot be simultaneously stable to deformations and discriminate features at large eigenvalues. We see here that if we want to discriminate between these two signals, one whose whole energy is located at lambda n-1 and the other one whose whole energy is located at lambda n, then we need filters that are narrow to separate both frequencies. But when we have a small perturbation, because the eigenvalues are large, they will fall outside of the passband in the perturbed graph, yielding an output of 0. This limits the value of linear filters in machine learning problems where features at large eigenvalues are important. The good thing about pointwise nonlinearities is that they preserve permutation equivariance while generating low graph frequency components which we can discriminate with stable filters. Essentially, the nonlinearity demodulates the signal, creating low frequency content that is stable. When we apply a ReLU to the signal located at lambda n, we see here that the new content in low eigenvalues does not change much. We also see that this content is different from the low eigenvalue content generated by the signal located at lambda n-1. This means that we can leverage this new low eigenvalue content created by the nonlinearity to discriminate between both signals. In essence, GNNs are stable and selective information processing architectures, whereas linear graph filters are not. As an illustrative example, let's consider recommendation systems. In the movie recommendation problem, we have a graph where each node is a movie and each edge is the rating similarity between movies. These rating similarities are estimated from the training set. Therefore, changing the training set changes the graph. Here we have a plot that shows the difference at the output of the GNN, whether it was running in the original graph S on which the GNN was trained, or if it's running in another graph obtained from a smaller training set that is a graph that has more estimation error. In essence, we see that the difference is much lower for a GNN trained with integral Lipschitz filters. Thus, such an architecture is more stable to graph estimation error. This was a very brief illustrative example, but you can find more examples of the importance of stability in these papers down here. Developing successful machine learning on graphs requires architectures that scale, exploit the structure, and have a distributed implementation. Graph neural networks achieve this by using graph convolutions followed by pointwise nonlinearities. I proved that GNNs are permutation equivariant and stable to changes in the graph, which leads to scalability and transferability. And I also showed you that linear graph convolutions are either stable or selective, but cannot be both, and that the addition of the pointwise nonlinearities makes GNNs be both stable and selective information processing architectures. I have briefly illustrated these stability properties in the problem of movie recommendation, where I showed that GNNs are stable to estimation errors in the rating similarity. Available online is the journal version of this paper. Thank you very much for your interest. Please do not hesitate to write me an email with any further questions that you might have. Thank you.